Okay, in this video we're going to be looking at capacitors, and in particular we're going to be looking at how a capacitor discharges through a resistor. Now, just to remind you, a capacitor is a device that stores charge. Now, it's basically made up of two plates separated by an insulator. It could be a vacuum or it could be an electrolytic insulator. Now, the capacitor is defined as it's defined by the equation QVC. Okay. Now this stored charge Q will increase with voltage, so it's charged by a voltage. Now obviously you can rearrange that equation to give you C is Q over V. Now in this particular video we're going to be looking at how the capacitor will discharge through a resistor. So in a circuit like this, it can be charged by a battery or a power supply, and then that can then be switched potentially to a resistor to allow it to discharge. Now as it discharges, it will lose charge, obviously. And the charge that it loses is equal to current times time. Okay, so the charge will affect the current, because the more charge it has, the faster the current will flow from it. So if we look at some basic equations, we've got Ohm's law, which can be rearranged to give the current, and that then links with charge being voltage times capacitance. Rearranged, we can substitute the voltage in. So if we take this I is Q over CR, what we're going to do is we're going to call the current the flow of charge. And now this flow of charge is a differential equation. We can solve the differential equation and we've got a nice new equation to use. So I've got flow of charge rather than current now, and that's equal to minus Q over CR. Now it's minus because the charge is flowing out of the capacitor. Now what I do is I take the Q from one side of the equation to the other, and I take the dt to the other side of the equation as well. So I'm swapping, and it's called separating variables. Both sides are then integrated with respect to dq and dt. So I have log of q, 1 over q integrates to give log of q, and that's equal to minus CRT. Okay, those constants when integrated with respect to time give a time, a linear pattern, a linear relationship, and I get a constant of integration. Now that constant of integration is going to be useful, it's needed. So what I do is I exponentiate both sides, raise it to the power of e if you like, and that allows me to do some rearranging. Now using my laws of indices, I can take the e to the c out, and now I can find what e to the power of c is by using initial conditions. Now my initial conditions are that my charge is equal to some initial charge, and so initially when time is 0, e to the power of minus 0 is just 1, so that term cancels, leaving me with the initial charge is equal to EC, and that then substitutes back into the other equation. So very quickly going through it, I hope you find it useful. If you need to go back and watch the video again.